In this section, we're going to talk about vaporization and the two forms of evaporation and boiling. Before we can do that, though, we need to talk about what pressure is and the different forms of pressure. Pressure is actually the force per unit area that is created as gas molecules collide with objects. And it's usually measured in newtons per meter squared, but in chemistry, we use atmospheres or millimeters of mercury as the unit. So our atmosphere is made up of air, and air is a mixture of gases. And we just talked about how gases, when colliding with objects, build pressure. So atmospheric pressure is the force per unit area exerted against a surface by the weight of the air molecules above the surface. You can actually see in this diagram down here what we're talking about. The more air molecules above the surface, the more molecules will be able to exert a force, and thus there will be a higher air pressure. So down closer to the surface of Earth, we're going to have a higher atmospheric pressure than we would higher up. At sea level, atmospheric pressure is equal to 1 atm, or 760 millimeters of mercury. When liquid molecules convert into gaseous molecules, those gas molecules can then collide above the liquid. This is known as vapor pressure. One of the things that we have learned is that the weaker the attractive forces are of the liquid, the more vapor pressure will be above the liquid. And that's because it's going to be easier to break the attractive forces when they are weaker than when they are stronger. Substances that have weak attractive forces holding them together will actually have a higher vapor pressure, and we term those substances volatile. You might think volatile means explosive, but in chemistry, it means a substance that has a high vapor pressure due to the weak intermolecular forces holding them together. We just mentioned that there are only two factors that control the vapor pressure of a liquid, nothing else: temperature and attractive forces. If we take a look at the diagram to the right, you will notice that there are four substances: diethyl ether, ethyl alcohol, water, and ethylene glycol. You will notice that the x-axis is temperature, and as we increase the temperature of any of these substances, the vapor pressure of any of those substances will also increase. Think about that. As you add temperature, which is kinetic energy, to the molecules of the liquid, they can break free from their attractive forces with more ease. In a few slides from now, you will learn that when the vapor pressure of a liquid is equal to the atmospheric pressure surrounding the liquid, boiling point will occur. If we focus our attention on 760 torr, which is also 1 atmosphere of pressure at sea level, if we go across the graph and intersect each one of the lines, you will actually be able to record the normal boiling point of the liquid. Notice that water has the highest boiling point, whereas the diethyl ether has the lower of the three boiling points. That's going to be due to the attractive forces of the liquid. We will learn that water has one of the strongest attractive forces holding the molecules together, and that is known as hydrogen bonding. Vaporization is the conversion of a liquid to a gas. There are two forms of vaporization. The first one is evaporation. Evaporation occurs spontaneously at all temperatures at the surface of the liquid. The molecules of the liquid break free from their attractive forces as they absorb the natural energy of the environment. Only the molecules at the surface have the ability to do this. Boiling is the other form, and that's when we add extra kinetic energy known as heat to a liquid. Within the body of that liquid, the molecules will then start to separate, break from their attractive forces, and will be able to convert into that gaseous form. We will learn that boiling occurs at only one temperature, dependent upon pressure. In the last presentation, we learned that boiling point is the temperature at which a liquid can convert to a gas. And that is true, but there's a better definition that we can apply to boiling point. Boiling point is actually when the external atmospheric pressure equals the vapor pressure of the liquid. Remember that the force of molecules in a liquid escaping and entering the air is called vapor pressure. We don't normally notice the vapor pressure of most liquids because they're a lot lower than atmospheric pressure. Let's take a look at the first beaker, and you will notice that we have water at 90 degrees Celsius. At 90 degrees Celsius, we find that water has a vapor pressure of about 525 torr. In comparison to the atmospheric pressure of 760 torr, the water's vapor pressure is not strong enough to push against the 760 torr of atmospheric pressure. Thus, only a small amount of the molecules in the liquid will be able to vaporize. In the second beaker, you can see that there is a tie between the air pressure and the vapor pressure of water. Because of this, we will start to see the liquid molecules converting to the vapor molecules with more intensity, and thus the process of boiling is occurring. We've learned as altitude increases, atmospheric pressure decreases. So what that means for us is that at various altitudes, we're going to have different boiling points of a liquid. A student in Denver, Colorado would measure the boiling point of water to be about 98 degrees Celsius, where a student in Charlotte, North Carolina would measure the boiling point of water to be 100 degrees Celsius. As scientists, we need to keep measurements like boiling point standardized. So the term normal is used to target a boiling point around 1 atm or 760 millimeters of mercury. When you ask that student in Denver, Colorado, what the normal boiling point of water is, they will tell you 100 degrees Celsius. Just as a quick tidbit, I wanted to direct your attention to Mount Everest and its altitude in feet, which is 29,000. Notice that the boiling point of water here is 69 degrees Celsius. This leads into a very important question. Does it take longer to cook food on Mount Everest than it does at sea level? Hopefully you said it does take longer to cook food at those higher altitudes. Remember, the thermal energy associated with 100 degrees Celsius is a lot greater than the thermal energy of 69 degrees Celsius. More heat means less cooking time. Students get really confused with this idea. There's this misconception that boiling means hot. It really is just the conversion of a liquid to a gas. But boiling takes place at various temperatures. It's the temperature, which is the measure of heat, which actually cooks the food.